Hello students, in today's class we will read about electrostatic potential. So we'll start the class over here. So first of all, what we are doing is that we are considering a static charge configuration. We are having one charge here which is static in nature, and another charge at some point which is also there, and we are not trying to move it at present, but that is a unit positive charge. Now we have done, this is our static charge configuration. This charge is producing electric field in all the radial direction. Electric field is being produced. Now, potential energy of test charge Q is defined in the terms work done on the charge Q. The potential energy this positive test charge will be the work done by the system to bring this charge from this position to the P position, from R to P. Whatever amount of work is done on it, that will give us the potential energy on charge Q. This work done is proportional to Q, since the force at any point is QE. Like if our charge is traveling in this direction, so if we want to define the force at this point, force at point C, it will be given as force equals to Q into E. That is how we give force, how we define force. Force is charge into the electric field which is being generated by the another charge present in the system. This charge is not producing this E. Here in this formula, F equals to QE. In this case, this E is not related with Q, but force is related with Q. Force is related with Q. So, this force will give us work done. How? We know that work done equals to force into displacement. So this force is under consideration, and then we have displacement. Now this force is having a relation with our small charge Q, small unit positive charge Q, and hence our work done is also related with the charge Q. Now to find the potential, whatever potential energy we are getting, we are dividing it with the small charge, dividing it with Q, so that the potential what we are getting is not dependent. P is not dependent upon the test charge or the unit positive charge, or whatever you say, the Q. Okay, it should not be dependent upon Q. That's why. But till the time we were discussing about the force, the work done, both these quantities are dependent upon Q. If the magnitude of Q is changed, the magnitude of the force as well as the magnitude of the work done will be changed. Coming to the third point, this work done is proportional to Q, since force at any point is QE, where E is the electric field at that point due to the given charge configuration. Work done per unit charge, the test charge, is characteristic of the electric field associated with the charge configuration. work done per unit charge. The test charge is characteristic of the electric field associated with the charge configuration. How does that is justifiable? W equals to force into displacement. What is the value of force? Force is given by charge into electric field, and then it is into displacement. So that's how work done in the particular given system is proportional to the electric field. Therefore, electrostatic potential due to a given charge configuration is written as, now this electrostatic potential in this given system is defined by work done. See, work done by external force in bringing unit positive charge from point R to point P. So I'll explain it. See, we are having a charge, one stationary charge which is having no relation with anyone. That stationary charge is present in the space. We are assuming it, okay? So the one charge is present very separately in a given system. This is our system. In this positive capital Q is present. Now at a distance we have a positive small q charge, which is a test charge. Okay, this is the distance between them. This test charge is present at some position R, and there is another position P. We will bring this small q to the point P. We need to bring it and reduce the distance between Q and Q. Our aim is to reduce distance between capital Q and small q. What will happen on doing that is that the system will do some work. On small q. This some work done on small q will be stored as the potential energy of small q. Potential energy of small q. Okay, so this potential energy of the small q is dependent on the work done by the system on the small q to bring it from the position R to position P. From position R to position P. So as soon as it is coming here, to find the potential which is for our charge q at point P, we tend to divide the potential energy stored by the small q by the magnitude of test charge or by the magnitude of small q itself. See over here, force is defined as QE, work done is defined as Fs, which is QES, and then we tend to define the potential in V as work done divided by the charge. So the work done over here will be considered in the form of the potential energy. Potential energy stored in the charge small q is equal to the work done on the charge small q. I'll again repeat, please make a note of it. Potential energy stored by the charge q is equal to the work done on charge q by the system to bring the charge from the position R to position P. Now work done by external force work done by external force. Here our small q is not doing any work. No work is being done by the small q. Work is done by the external force. F external is doing the work. In bringing a unit positive charge from point R to point P is given by the voltage or the potential at P minus the potential at R. We are simply calculating the potential for that charge at point P and point R. In other words, we can write potential energy at P minus potential energy at R divided by Q. Come to the bottom. Here UP is potential energy stored in the charge, potential energy stored in charge Q at point P. Similarly, UR is potential energy stored in charge Q at position R. What is potential energy? Potential energy is defined by the virtue of a position of any object under consideration for calculation of the energy. So it depends upon the position. At P it will be something else and at R it will be something else. So UP minus UR divided by the charge. So we made it charge independent. Okay, our potential is charge independent, where Vp and Vr are electrostatic potential at point P and at point R respectively. It is not the actual value of potential, but the potential difference that is physically significant. What does the physical significance means? This is not the potential energy. The work done can be defined at every point. So we are defining our potential with respect to the work done in that particular system. So this is physically significant. We choose potential to be 0 at infinity. What we did in the previous system is that we have taken our charge at position R and at position P. At position R we did not define our potential to be 0. But now we are taking our test charge to be at infinity. Infinity is very far from the capital Q charge. So what will happen? The electric field will start diminishing till the time they reach this infinity. So at that particular point we can define the potential to be 0. At that particular point we can define the potential to be 0. Then what will happen? Work done by the external force in bringing a unit positive charge from infinity to the point will be given as electrostatic potential at that point. In other words, the electrostatic potential V at any point in a region with electrostatic field is the work done in bringing the unit positive charge without acceleration from infinity to the point, to that point. Now see the diagram. This is our R position, this is our P position, and we are bringing our test charge from these positions. Like see, Q1, Q4, this is a system of charge. Okay, this is a system of charges, system. So we are bringing our test charge from this R position to P position. We are using many paths. This is a path, this is a path, this is a path, this is also a path. So there are many different paths. So though it is following up different path, what is the thing is that work done will remain same. Work done is independent of path followed by the charge to come from point R to P. Secondly, the potential is defined as electrostatic potential. See, the definition is given in the first point. It is electrostatic potential at any point in a region with electrostatic field is the work done in bringing a unit positive charge without acceleration from infinity to that point. So I'll write the highlighted point. Work done. First concept is of work done. Work done in bringing a test charge from point or from position R to P, or at this point we can write from point infinity to P, anything, to whichever point, to whatever point we want to define, that will be written here. Okay, and the main condition is that there should not be any acceleration throughout the course of the path that is being covered. Our charge should move with uniform speed. There should not be without acceleration. In the defined electric field. If there is no electric field, our small q charge will not face any repulsive force. No repulsive force will be forced. So then what will happen? No need to provide any work done. No need to provide work done. So what will it give us? It will give us no potential at all. There will not be stored any potential in the charge if there is no electric field. To obtain the work done per unit test charge, we should take an infinitesimal small test charge, that is Q, del Q, obtain the work done del W in bringing it from infinity to point, determines the ratio del W by del Q. Why we are taking the small charges and small work done is because we are considering a small system, and for that we are just defining over a small area in that the small system which is being formed, so that it is easy for us to define it, as our any system is not uniform. If we are taking a small system inside that big non-uniform system, we can say that this is approximately uniform. The defined smaller system can be approximately uniform, and we do not need to worry about these the leakages from the non-uniform surfaces. That's why we tend to take this smaller element. So here we took a infinitesimal test charge del Q, and for that we obtained an infinitesimal small work done, that is del W. So what we have read is that work divided by the charge will give us the potential. Similarly, the potential over here is defined as potential equals to small work done divided by small charge. Okay, so this is how we have defined for a small system. Also, the external force at every point of the path is to be equal and opposite to the electrostatic forces on the test charge at that point. What this aim at, like there will be some force in this direction, that is F due to electric field that is being produced by the capital Q charge, and when this charge is moving from here to here, it will have some force external which is helping our charge to move, from R to P. Okay, so this is one force, and other one is this force. Now this force at each and every point, these forces at each and every point should be equal and opposite. F external should be equal and opposite to force due to the electric field at each and every point in the path, in the defined path. So these are the rules and regulations, like force should be opposite, work should be divided by charge to make it charge independent, and this is the way we define electrostatic potential as well as the potential, or interconvertibly anything. Electrostatic potential is similar to that of the potential. So always remember, when we are dealing with the electric charges, capacitors and electrostatic potential, the term potential is used as electrostatic potential as well as normal general potential also. So these are not two different words, they are same. First concept here we read is the electrostatic potential. The another concept we read over here is the potential energy. These two concepts are quite different. Electrostatic potential deals with the amount of potential that's been held by the charge, whereas the potential energy gives the energy that is held by our charge Q at that particular position. If the position is changed, amount of potential energy that is being stored in the charge Q will also start fluctuating, will also start changing, because potential energy is the energy by the virtue of the position of a given object under the consideration of energy calculation. So that's all with respect to the potential energy. We'll move on to the next slide, where we will read about our scientist. One of our famous scientists which have a very important role play in making these batteries. So if he is not thinking in the way he thought, we may not have these batteries, we may not have these energy sources, and as there is no battery, there may be less development in the concept of electrostatic capacitors. The formation of battery and understanding of the concept of capacitance have a close link, okay. So who is the great scientist of the time is Count Alessandro Volta. He was on the planet from 1745 to 1827. He was an Italian physicist, professor at Pavia. Volta established the animal electricity observed by Luigi Galvani. So this Sir Galvani have seen these animal emitting energies. Animal emitting energies or animal generating electricity. Generating electricity. So according to Sir Galvani, these animals are emitting energy by the process of bioluminescence. Bioluminescence. Maybe they are having this property of emitting the light. What is bioluminescence? Is that biological objects which have property to emit the light. That is called bioluminescence. So Sir Galvani thought of this. Sir Galvani was there from 1737 to 1798. In experiments with frog was also generated whenever any wet body was sandwiched. Muscle tissues placed in contact with dissimilar metals. So what was the observation is that just make little space over here. What was their observation? That any wet body or any wet tissue, muscle tissues when are sandwiched between dissimilar metals. Dissimilar metals. See, here we have some metal A, and here we are having some metal B, and in this we are having a muscle tissue, Now this muscle tissue is being sandwiched between A and B. This will generate luminescence effect. Now this luminescence, how this is defined and how the principle behind this luminescence is given, what happens when this situation of sandwich occurs, and how these frogs are able to emit the light. All these things were explained by Sir Count Alessandro Volta. See over here, muscle tissue placed in contact with dissimilar metals was not due to any exceptional property of animal tissue, but between the presence due to dissimilar metal. So this led him to develop the first voltaic pile, a battery consisting of large stack of moist disc of cardboard, electrolyte, sandwiched between the disc of metal electrodes. Now how Sir utilized this knowledge to make something new is that he made the voltaic pile or the voltaic batteries. See over here in this figure, they have given us these batteries ka diagram also. So in these voltaic batteries, what was the construction? We had one electrolyte solution stored. We have an electrolyte solution stored here, and on the side, both these sides, we have placed two metals. Over here we placed metal 1. It can be aluminium, copper, zinc, and on the other side we have placed the another metal. Again it can be aluminum, copper, zinc, anything, but these two metals were different. Metal A and metal B are dissimilar. Our tissue have so many ionic composition. Ions keep on moving here and there. If you go and read about the muscle tissue, you will find that muscle tissue have lots of ions in it, like potassium and sodium ion, which help in the excitation and relaxation pump of our muscles. And our muscles work on the basis of release of calcium 2+ ions. If these calcium 2+ ions are reduced in our muscles will start feeling fatigue. Okay, so these many ions are there. These ions keep changing from here and there. That's how this muscle tissue, when are kept between metal A and metal B, behaves like an electrolyte. So if you are studying physics, to understand this biological importance also you should have a little knowledge of biology. And if you are studying biology, the vice versa principle is applied over here. All the disciplines of our science subject are interconnected. To understand a single topic, we need to have knowledge of all the disciplines of science. So all are equally important and everyone should have equal knowledge of all the subject. I'm not just saying that you should have all the knowledges from all the subject, but you should have the minimum needed knowledge of all the subject to study in a single subject of science. Okay, so this is how the muscle tissue works, and this knowledge was with Sir Count Alessandro Volta, and he have used this knowledge that muscle is equivalent to an electrolyte. He generated one electrolyte, kept in between the metal A and metal B, and made it a voltaic pile. And he did a milestone discovery in our race of getting electricity, in our race of storing electricity. He made a very big discovery. So this was our battery system, which was generated by, which was understood by Count Alessandro Volta sir, and then sir gave it a defined shape with the help of non-living things, or with the help of electrolytes and the metals and the element which are present, which can be made use to produce such things without harming any living body. So that's all for today's class. We'll come up with a new topic in the new class. I hope today's class was fruitful for you and you have learned a little about our scientists, our physicists who have done so much in the field of physics and generated and made the physics what it is today. Okay, bye bye, have a good day.